see how this contraption really works and if it would eventually stop. We checked its movements and recorded its position, velocity, and acceleration to see if there is some trend in the motion. We placed the origin at the center of the cradle. Also, the point mass is going to be in the middle of the two balls on the ends of the cradle, since the transfer of energy from the balls is too quick for us to include the other balls in the point mass. So let's look at the first graph, which is the position time graph. We see that this graph has a clear trend of an upward and downward slope. This is pretty obvious because the ball travels from the negative coordinate of x to the positive coordinate of x and back again, as seen in the video. The next graph, which is the velocity time graph, shows us another trend, that the ball's velocity from the start speeds up, and as it hits the ball, it becomes constant. Then it does the same trend, albeit going downward. Then this continues again and again. This graph shows us that the ball, as it hits the next ball, doesn't stop, maintaining its speed before the ball on the other end speeds up with the same velocity trend as the last ball, although negative, and it swings back to repeat the sequence. As seen on the graph also has a pattern, in which it gradually accelerates as it swings downward, and as it nears hitting the next ball, it decelerates but only for a short time, as it accelerates again after hitting it and making the other end of the ball swing, and this ball clearly mimics the motion of the last ball, thus the graph continues with this trend. So with all those data aside, we go back to one of our main questions. Will Newton's cradle ever stop? Well, after some research, our answer to that question is yes, it will soon stop. Although its velocity, position, and acceleration graphs produce a pattern that barely changes, the concept of friction changes this. The energy that is transferred is somewhat intact, but some part of it is lost because it has been converted to heat by friction. The reason we can't observe this in our graphs is because the energy lost is too little to be obvious for a short period of time. Also, according to sources, the time it takes for it to stop is about 1 minute and 50 seconds. So Newton's cradle does support the laws of action-reaction and the conservation of energy plus momentum, since the balls were nearly constant with their movement. And even if the balls lose energy, it is still converted to different types. Now we go to the homemade setup. So we made this setup also to test some concepts of action-reaction and if the height of an object would affect the force it exerts in a pendulum motion. The setup looks like this. A ball is strapped on the end of the plank and a toy car is placed just below the end of the plank. After that, the ball is lifted on an angle depending on the height, and then it is dropped from that angle to hit the car. The motion of this ball will then be tracked to see if it would exert less or more force. We also will track this motion by placing the origin on the ball to get it on the x-axis perspective, and set the point mass on the middle of the ball. We also plan to track the car's movements afterward to compare its position, velocity, and acceleration after taking the hit. So now let's look at the data we gathered from the first ball on the 7.5-inch height. We see that in our position time graph, the ball's displacement was a gradual slope to the left, meaning that when we look at its velocity graph, it is speeding up and accelerating at a normal rate. However, if we look at its acceleration graph, we see that indeed it was accelerating. However, when the ball reached the top of its pendulum axis, the ball's acceleration decreased. So since our goal is to find if height affects the pendulum's force, we need comparison. Thus, we need another trial which included the ball being lifted on a higher height, which is 13 inches. After tracking the motion of the higher ball, we get to see in our position time graph that the travel downward was much steeper than that of the early trial. So that alone means that the velocity of the second experiment was much higher than the velocity of its previous trial. So those data can lead us to infer that the acceleration advantage would also go to the latter. To further prove and test the results that we have gotten, we decided to track the movement of the car after being hit. The data we gathered from the track showed clearly that the car moved faster and was displaced more than the car which was hit from a lower height. Thus, it is valid from our experiment that the higher a pendulum is dropped, the higher force it is going to exert. So this experiment says a lot about the laws of inertia and action-reaction, because the car's displacement was affected by the force of the ball, and also the car did not exert the speed and displacement of the ball because its inertia resisted some force. So there you have it, folks. I hope you learned something after watching this video. I'm Matthew Manalo, and together with my groupmates Cedric Marcos and Miguel Sison, we thank you for watching this video, and Godspeed. Also, don't forget to comment below for any suggestions or angry reactions.